Alright, so this is what we were doing in the last class, and we were talking about these things, right? So how do you get, right, so let me just scroll. Right. So we said that this is transformer architecture, this is the encoder part, right, and then there will be decoder part. Okay. So in encoder part all you have is self attention, in decoder part you have self attention as well as the cross attention. Okay. So we will talk about that now, and right. Any questions on this particular equation? Okay. Now this, if you see, is same as what we did before in attention, right? This is not different from that particular thing, and so how do you compute this? Let me, so I'll come back to these things. I'll come back to these things because see, Q, K and V, here we need parameter matrices, so we rather write them as WQ, WK, WV, right. So these are the parameter matrices. How are you going to get these three vectors, right? So let us say you start from here. So now we are going to talk about these three vectors. What is the, so how many elements here? This is called the D model, which is there in the transformer paper actually. So D model for transformer in attention is all you need is 512. What does this mean, D model? D model means I will have from x1 all the way to x of D model, which is 512. If you change this to 1024, then I will be taking x1 to x1024. Okay. Now each x1 is, so see this 512 is repeated. D model is 512 means you have 512 inputs here. 512 x's here, x1, x2, x3, and each element is 512 size vector. Okay. So what you have here is 512 elements and everyone is 512. Now what transformer achieves is all these 512 computations, they can happen in parallel. So you can feed all 512 words in parallel. Okay. Now there are a few things that we won't do in this class because we just don't have that much time, and they are details, still things under research whether they are needed or not needed. So what I will do is I will first write. So tell me one thing before I do that. Tell me. We will come to that. So of course in the end when you feed something to neural networks, they have to be embeddings. So they are embeddings, right? And that was the precisely question I was asking, what are x1s? See, remember LSTMs were solving this problem. Why do we need transformers? Which problem triggered us to go to transformers? So we saw that in decoder, in encoder decoder of LSTMs, there was just too much reliance on this one vector, right? And the problem with this is this one vector has to encode the whole sentence however big, right? and that also suffers from vanishing gradients. LSTMs don't suffer that much, but still they are RNNs and they do. Okay. Now, another problem with RNNs was, see, there were two problems that you should know. One is too much reliance on that vector, another one is RNNs are inherently sequential. Once you choose an example to train on, you will first compute x1 and then hidden state for the first timestamp, then you will go use x2 and the hidden timestamp here to compute the hidden timestamp at the hidden state at timestamp 2 and so on. That is inherently sequential. What transformer does, you give all 512 elements in parallel. This is a huge difference. Okay. This is encoder, you give all 512 elements in parallel here. Now, what are these x1s? What are the things that we are missing which we had in LSTMs but not here? So, LSTMs had an advantage over this. What was that? You see here, when we say all these things will be processed in parallel. So, this line of computation is an independent one and you have 512 such independent computations going on in this direction. Okay. Are they sequential in this direction? This direction is sequential. You can't, you have, so encoder 2 has to wait for the output of encoder 1. There you can't do much. So, if you see, it's a deep neural network in this direction. Okay. Wherever deep neural networks come in, we have a vanishing gradients problem, and the solution to vanishing gradient problem we have given which one? ResNets. So, ResNets will come here as well. Okay. And I will draw this diagram that is there in the paper itself. So, ResNets are used to solve vanishing gradients in which direction? In this direction, in this vertical direction. Horizontal directions, all these elements are parallel. Okay. You process one. So, when you are processing x1, you can exactly simultaneously process x2 and x3 and so on. So, x1 to x512 will all be processed in parallel. This is a huge thing that transformer comes with. But tell me, if it is so much parallel, x1, x2, x3, x4, x5, if I take any permutation of this, will it still be the same? LSTMs had an inherent notion of timestamp. First you will process x1, then you will process x2, then you will process x3 and so on. So, that way sequence was enforced by structure. Now, here if you see, we are saying all 512 are in parallel. Now, you are not enforcing structure. Now, this just becomes a bag of words, right? There is no sequence as such. So, the sequence property is lost. What authors do to regain that is, so let me draw the complete transformer architecture first. I mean, I should have started from the paper itself yesterday only. So, let me first draw the transformer. So, if you see here, we start with so these are input embeddings. Okay. Now, you take input embeddings, you simply add something called positional encodings. Okay. And then that becomes your actual x1 that you feed. Now this is your we are doing two diagrams, one as it was there in the JLMR's blog. Right now I am drawing it from transformer paper, this famous figure that you might have seen I do not know how many times. Okay. So you have this multi-head and then this goes to add and norm, and then this goes to feed forward neural network, which again goes through add and norm. And what is this add here? So this is your one encoder as shown in the famous paper itself. Okay. And then finally this output goes to, we will see. So my question for you is, what is add and norm here? Okay. Add means your skip connections, so you just add them. Okay. Skip connections added. Norm means you layer norm, you normalize the layer. Normalize in the sense, see, when your outputs come, they can be whatever, right? You do not want them to give whatever distribution, you want to enforce some kind of distribution, let us say Gaussian distribution. Okay. So that stabilizes your training, and that is why they are here. Why is this add here? Why do we have this add here? Add is because of the skip connections. Okay. So encoder, this is something that you do 6 times. Now the last one is going to give you this one. Okay. I go and draw the decoder as well now. So these are the output embeddings. And then again positional embeddings. What is the role of positional encodings? Yes, what is the role of positional encodings? Right. So the role of positional encodings is that the transformer way of doing things. So how many inputs are here? Even though we have drawn just one, how many actual inputs are here? 5 and 2. In general, D model. For transformers in this paper, D model is 5 and 2. It changes for other. So this is fine. Now we had something called masked multi-head attention. Okay. Then again you have add and norm. Add and norm basically means, so this one goes here, Now this is different what comes. Okay. Now what you have is you are coming so two things are coming from here now. Okay. This guy goes up and is fed later as well. So let me just draw multi head. Multi-head attention, and this one goes here, this one goes here, this one goes here, and what you have is this one also goes here, which is your addendum. Feed forward neural network. I hope everybody is drawing with me. मतलब मैं अकेला ही नहीं बना रहा हूँ. Addendum. Since there is addendum, so after this addendum you go and add this one as well. Okay. Then there is this linear. Then there is this softmax, and then that gives you the output probabilities. So this is what we have as transformer network. That's what I am trying to do. अच्छा overall ही right. Let me keep it aside now. यार ये but ठीक है, it is worth. Right. So this is what we have. I can right. So this is what we have, the transformer, the famous transformer architecture. Now, so this thing is not connecting here. So what you have is Q and sorry, not Q, K and V's will be coming from here, and this is your 1, before linear, this is your decoder, this is your encoder. So let me just so this is our encoder, and this is our decoder. Right? What we have done until now is, so we are talking about this thing, multi-head attention. Positional encodings, I will simply state, go and look as they are in the paper. They use sinusoidal waveforms to do this, but for our class, positional encoding simply means you have this, what is this? Input embedding. What is this input embedding? Your normal embeddings, right, that you, for example, word-to-vec embeddings, even though you don't do that, you don't use word-to-vec here per se. Positional encodings, you just, so what will be the dimension of positional encodings? Remember, you are adding them here. So they have to be 512. If input embeddings are 512 dimensional, they have to be 512 dimensional. You add them and you feed. What is the purpose of positional encodings here and here? They maintain the sequence, right? They somehow magically do this. There are papers that say you don't really need them. There are papers that say you need them and you actually improve it compared to what they have in this particular thing, right? So for our purpose, we simply have positional encodings that help us retain the sequence. Okay, and how do we achieve it? By simply adding it to the input embeddings. Now this is seen as a magic. Why? I have input embeddings, I add something to it and it happens to retain the sequence. That is so counterintuitive because all you are doing is just adding some numbers here, right, and it is still able to do that. So I mean, after addition it will still be a vector of 5 and 2, which could have been just my input embedding, but no, this plus that you do actually seems to have impact, at least in this paper. And then there are so many things that you also study, right. So there are so many variations of positional encodings, but we don't go into this. All we talk about is, once you have prepared X, what do we do now? Yes, once you have X here, how many such layers are there? 6. So let us just talk about this first one. Remember, this one, this multi-head attention is nothing but what we yesterday called self-attention. Okay? So you have self-attention. What were the equations for self-attention? Now everybody agrees that we have input X here, input X goes in. How do you compute QKV? Why do we need QKV? Remember, in attention we had S, H and V. S and H were different vectors coming from two different RNNs, and V was a linear combination of H's itself. Okay. So here we come, X, how do we compute Q? WQX. So since I am talking about Q1 for the Q vector for the first one, let me call it just Q1, and actually these are these guys. So let me just keep it that way. Later I may just start calling it Q1, okay, but this is what we actually mean. Now how do you make K1? WKX1. How do you make what is left? V1 okay. Now what will be the dimension of WQ? Q1 is a vector of size 64 cross 1. This is a vector of size 64 cross 1. This is a vector of size 64 cross 1. Yes. So this has to be 64 cross 512. Okay. So this has to be 64 cross 512. Now See, now the way they are doing operations is they are doing it the other way around. Okay. So they take x here. So just to follow their notation, what we'll do is, let me just do that because otherwise later I'll be in trouble. So I'll simply use this one. This is contrary to what we have been using throughout the class, but since we are towards the end of it, okay, let's just do it. So now if this is 64 cross 1, what is this guy? This is 512 cross 1. What is this guy? नहीं रुक जाओ मतलब नहीं, let me just follow the thing that we have been following throughout, and if there will be issues we'll resolve it there. Okay, let's keep it this way, but keep your attention is all you need, because I might make mistakes here. So now this becomes 64 cross 512, and this guy is 512 cross 1, so that gives me 64 cross 1. Similarly for all of these guys. Okay. So I have these things now as before and done. What next? I have Q1, K1, V1. This is coming from X1. X1 was 512. This guy is 64. Let's leave that right now. So how will I compute the output? These things are happening at which level, which place? Have we computed the self attention yet? No, we have not computed the self attention. So how do we compute the self attention? This is something that we did yesterday. Remember that equation and those things I had drawn? How do you compute the self attention in this case now? Yes. So I have Q1, I have Q1, K1, V1. How do I compute the self attention? What was the formula? Softmax, and let's forget that formula key, it was QK transpose, right? All you need is, you need to take dot product of Q and K, is that right? Yes, Q and K, normalize, do softmax and then multiply with V. Okay. So how will I compute self attention in this case now? What do I have? I have Q1, K1, V1. What else do I need? What else do I need? In order to be able to compute self attention, what do I need? Self attention कैसे निकाल गई तो बताओ भाई? Which one is S in this case? Q, right? That is your query vector. Query vector has to take dot product with all the keys. Here you have just one key, so I can't really do that operation. What else do I need? I have 512 X's, so for all of them I will do the same operation. I will compute Q of 512 as WQ X512, and similarly I will compute K of 512. See, right now I am not doing in the vectorized form, I am not doing it in the form of matrices. Okay, that gives us X 512 and I am not writing the last one, right? You write that. Now tell me, how will I compute self attention? How will I compute attention? Forget self. Yes. अब आसान है भाई. If you are not answering, that means you are not paying attention. Yes. So see what the figure that I have here. Now I am zooming in here. Okay. So when you zoom in there, you have 5 and 2 things. What are the 3 vectors here at the position 1? I have q1, k1, v1. I have q512, k512 and v512. I have q1, k1, v1, I have q2, k2, v2, I have all the way until, so how many numbers here and how are we getting them? All of those are obtained by doing a linear operation on my input embeddings plus positional embeddings, right. So what are these x's here? They are my input embeddings plus positional encodings. How did I get q1, k1, v1? We have written that. So q1 is wq times x1, k1 is wk times x1. So all these are coming from x1, all these are coming from x2 and all these are coming from x of 5 and 2. Okay. The parameter matrix that is sitting here is wq, wk, wv. Same wq, wk, wv. Okay. Right. So this is what we have. What do I do next? How do I compute attentions? So what will come here now? I am taking attention. So which one will be pivot and we will move on which particular variable here? So the way we were computing attentions earlier was q1 now so this is my q1 dot k1. What will be the next thing? q1 dot k2. This is how you did it. S1 dot product with H1, S1 dot product with H2, right. So all the way until q1 dot product with k512. Done. So this is what we have. What is the length of this vector? This is 512. Okay, 512 dimensional vector here we have. So what was this called in, whatever it was called in earlier terminology, fine. What do I do next? Remember what was the formula for self attention? Q, K, forget transpose, we are doing it this way. So Q into K divided by under root of dk, dk is 64 in this case. So this is actually, this is our dk, this is what we have. Okay. What do I do next once I have taken these dot products? Yes. So once I have taken these dot products, I normalize. I have to divide it by under root dk, but I am keeping that aside for the time being. Actually you can just divide by 8 because under root of 64 is 8. So divide by 8 and then take softmax. So divide by 8 everywhere and now take softmax. Okay. So 8 is basically under root dk in this case. So this is what we have. Now I'll give you the computation for this and then we take a break. So tell me, how many elements here? अभी रुक जाओ, मतलब अभी अटेंडेंस ही हुई, आ जाओ आ जाओ आ जाओ आ जाओ. हाँ, Q1 K1, how many elements in total? 512. Okay. So 512 we have, divide by 8, normalize, basically take softmax. Now you have a probability distribution, right? What do I do next? I have this vector of size 512. I have this vector. What do I do with this? What is the last operation left? Multiply with V. Yes. Multiply with V means? No, but what is V? What is the dimension of V? How many V's do I have? As many as Q's and K's I have, right? So this part will be coefficient of V1, this part will be coefficient of V2 and so on, right? So you have a vector of V1 all the way to V512, right? This guy gets multiplied with this guy gets multiplied with this. What will be my final output? So what is this particular vector? This is 512 cross 1, is that right? 1 cross 512, thank you so much. This is 1 cross 512. And what will be that V thing? So if you have here, I will have V1, sorry, not in this manner, we are writing it in this manner, V1, what else? V2, all the way until V512. What are the dimensions of this matrix? This is 512 cross 64, because each V1 is, each Vi is 64. Right? Resulting thing is 1 cross 64. Now remember those transpose is coming into picture. So finally we will have to make it 64 cross 1 again, that we will see. Okay. So finally you have computed what? This is, now we take transpose of this because we were supposed to do that somewhere. We take it here and that gives me 64 cross 1. Okay, that gives me 64 cross 1. What do I do with this now? What is this output? What is this guy? यार I thought मैं continuously आज खत्म कर देता, but 11 बजे you have a class. Yes, so that कल आना ही ना पड़े ना आप लोगों को ना मेरे को. Yes. What is this 64 cross 1? You answer and we go for a break. You don't answer, we don't take break. Huh? This is self attention. This is the output of my self attention layer. So, write it down. This is the output of first. We take a break now, or break not needed.